Hello guys, welcome once more to another video in our YouTube channel. So in today's video we are going to be looking at the topic application of calculus, and we are going to be solving the problem that is being displayed to you. So I'm just going to read the equation. It reads: a particle moves along a straight horizontal line with acceleration a sine omega t at time t. Initially the particle is at rest at O on a fixed line. The displacement of the particle from O at time t is given by, so the objective is to find the displacement, otherwise called the position vector of the particle from the origin, yes, at time t seconds. So we are going to get the relationship between the acceleration and the velocity as well as the displacement. So first we are going to get the relationship between the acceleration and the velocity. So our acceleration is simply given by dv by dt. Alright, so that's a basic recall that we need to know. Acceleration is equal to dv by dt. So in this case we have the acceleration already. The acceleration was given as a actually the a that has, they said a sine omega t. The a that is given from the acceleration. Let me just try to replace the acceleration with ac, for example. So that's the acceleration. So our acceleration in this case, our acceleration is given by a sine of omega t. Alright, so it means that our a sine omega t will give us what? Dv by dt. Now this what we call a first order differential equation, where you can separate variables and integrate. Now to separate variables, I'm going to pair all the variables that are in terms of t, and I'm going to pair all the terms that are in terms of my variable t, and all the terms, or that's all the functions that are in terms of my variable v, and then I integrate separately. So I see that just dv is with v, and then I can cross multiply with t. I'm going to get a, the sine of wt times dt. I've succeeded in separating the variables. Now doing that, I'm going to integrate both sides of the equation. So integrating both sides of the equation, remember that we are dealing here with indefinite integrals. So with indefinite integrals, we need to add our constant of integration. So integrate the left hand side, meaning I integrate dv, and I'll integrate the right hand side. Now my a is a constant, so I pull it out of the integral. Now the function there is sine of omega t. I'm integrating it with respect to t. Okay, so when I integrate the left hand side, which is dv, I'm just going to get v. But since it is an indefinite integral, we need a constant of integration. So I have v plus a constant of integration. Let me just say c1. That's for the left hand side. And then the right hand side, when I integrate, I have my a there. Now when I integrate a sine omega t, I just have -1 over, I differentiate omega t to give me omega, then I multiply with a cosine of omega t. Alright, I multiply with the cosine of omega t, then I also need to add another constant of integration, because the right hand side as well is still an indefinite integral. Okay, so with that said, now let's see what we can do with our constants of integration. So the left hand side, I'm going to get my left hand side, I have v equal to, now the right hand side, I'm going to write this as -a over omega, the cosine of omega t, then plus I'm going to subtract c1 on both sides, so I have c2 minus c1. But now c2 minus c1 is still a constant of integration, right? So c2 minus c1 is still a constant of integration, so I'm just going to now call it c. So this means that it means my v is equal to -a over omega, the cosine of omega t, then now plus just a constant of integration, because c2 and c1 are constants. It means that they are different, so you give me a constant. I just call a constant c. Now we need to get this constant of integration. Remember that our objective is not to it's not to find the velocity, we need to find the position vector, that's the displacement. So in order to do that, we have to in order to do that, we need to get the velocity, then we get the displacement. I'm going to show you another way that we could move from the acceleration to the displacement automatically, but now it's going to we are going to have a little problem there, and I'm going to show you guys why that method is not going to be the best here. Okay, now we need to look for that constant. Now let's go back to the equation. It says initially the particle is at rest at O on a fixed line. O means O generally refers to the origin. Now when you're at rest, it means that what? At rest means time is 0 and the velocity is 0 as well. That's the meaning of at rest. So time being 0 and the velocity being 0, so let me just write down the condition here. So we have that at rest t is equal to 0 and v is equal to 0. T equal to 0 and v equal to 0, we can look for our constant of integration, right? So it means that my v, which is 0, will give me negative a over omega, the cosine of omega times t, which is 0, then plus the constant of integration, which we are looking for, plus c. Now from there we can be able to get c. Now the left hand side of the equation is just 0, but now so we are going to get 0 is equal to cos 0 is 1, because omega times this is actually the angle, which is omega times 0, which is 0. Now cos 0 is 1. Here we have times negative a over omega, just gives us negative a divided by omega. So we have then now plus our c. So it means that our c will just give us a divided by omega. So it means that our c is going to give us positive a divided by omega. That means c is equal to a divided by omega. Now having c as a divided by omega, now we are going to replace it back into our equation, right? So we are now going to replace it into our equation, and this is what we are going to get. So let me just increase the text box. Now having c as that, I now come back to my equation. So I now come back here and I replace the value of c with a over omega. So it means that my v will be equal to, in the place of c here, I replace it with its equivalence, which is a divided by omega. Alright, so replace c with a divided by omega. Okay, I've replaced it. Now I've gotten a, right? Now I can factor out the a divided by omega, and then I'll be left with negative the cosine of omega t plus 1. Okay, this is what I have. Now let's now link the velocity with the displacement. That's the velocity with the position vector. So the velocity is simply given by the derivative of the position vector with respect to time. That's the velocity. So it means that if I multiply both sides by dt, I'm going to get the arrow is equal to v dt. So the arrow being equal to v dt, I can now integrate both sides. It means that the integral of the arrow is simply going to give me the integral. Remember, it's indefinite. Now in the place of v, I'm going to replace it with this. Alright, then I multiply it with dt. So I replace v with this, and then now I'm integrating with respect to t. Okay, so with that said, it means that if I integrate the left hand side, I'm going to get I'm just going to get arrow, but plus a constant of integration. Maybe I can call it k1, for example, this time around. Now we need to integrate the right hand side as well. Now the right hand side, a on omega is a constant, so I'm going to pull it outside. Sorry about that. So k1 equal to a over omega is a constant. I'm going to pull it outside. Now when I integrate negative cos, anyways, let's integrate 1 first. When we integrate 1, we just get t, because we're integrating respect to t. Now when we integrate negative cos omega t, the negative sign remains negative, then I have 1 over omega times the sine of omega t. Alright, that's what I get. Then plus another constant of integration, I can call it k2. Now I can just move k1 from this position to the right hand side, right? And then now I subtract the 2 as I did here, and I just call the constant k, for example. So I'm just going to remove k1 from here, and then I'm going to remove k2 from here. Remember that I'm taking k2 minus k1 to give me my constant k. Okay, now we need to look for this constant k as well. We need to look for the constant k. So we apply the same condition. If you're at rest, it means that time is 0. It means that you have not moved any distance, you have not covered any distance, so your displacement is 0 as well. So we are going to use that very condition. So at rest, time is 0, velocity is 0, automatically meaning that the displacement is 0. So at rest, our time is 0 and our arrow is equal to 0. So doing that means that we can get the value of k. So in the place of arrow on the left hand side, I'm going to put 0 equal to a over omega. Now I have t, which is 0 minus 1 over omega, the sine of omega times 0 because it's t. Then now I need to add it to k. Now this one is just going to give us 0 because sine of 0 is 0. So 0 minus 0 is 0. We multiply it with this, we still get 0. So it means our k simply gives us 0 because the left hand side of the equation is 0. So it means that our k is equal to 0. So k being 0, now we have things are now good. Okay, so our k being 0, now we can now simplify things very well. So k being 0, right, we simply need to come back to our equation. So k being 0, we can now come back to this, right, because we are looking for the position vector, that is displacement. So we come here and we replace k with 0. So k being 0 there, we just come in the place of k, we fit 0. It means that we just need to wipe it out. So at the end we can multiply all through by a over omega. So it means our arrow is going to give us a over omega times t, then minus a over omega squared, sorry, it's supposed to be w squared or omega squared, then times the sine of omega t times the sine of omega t. So that is the value of the position of the displacement from the fixed position O at time t seconds. So let's come back to our responses and verify what we have. Let me just copy the answer and then we verify what we have as well. Okay, so let me paste the answer down here. Sorry about that. Okay, this is what we have. It's our response. So let us verify the answers that we have here. The first one says a over omega t plus a over omega squared sine theta. Our sign is minus, that's minus, so option A is wrong. Option B is perfectly okay, so option B is correct. So that is a displacement of the particle at time t seconds. Alright guys, so hope you loved the video, even though I was typing. Maybe it was not so fluent, but I believe you understood the concept from the concept that I'm applying here, that is simple integration but using initial conditions to get my constants of integration. So hope the concept is well explained. If you love the video, make sure you like the video, share the video with your friends, subscribe to the channel as well, and turn on your notifications after subscribing so that whenever videos are uploaded you always be notified to come and watch. Alright, thank you for watching. If you're watching the video and maybe you want to learn how to type using Microsoft, present your video as I'm doing like this. Maybe you're in a university and you want to get into YouTube, you can check the description of this video. You're going to see a link to the MAFA Microsoft training program, where there we are going to be teaching people how to use Microsoft, draw diagrams, and as anything concerning Microsoft programs, whether Microsoft Word, Microsoft Excel, PowerPoint, and others. Alright, so thank you for watching, and see you in the next video.